that originally had so 10 components in the GAB. We split this in terms of labs shift. So it's 1 plus 3, 4, plus this hij 6. So we end up with the 10 components here and kind of recast in this particular way. That allowed us to make explicit our coordinate freedom and then have a geometric interpretation of how we're going to think of the evolution. Then Einstein's equations can be rewritten in terms of the time derivative of that h related to this extrinsic curvature k, and then the extrinsic curvature rate of change is related to the Ricci scalar associated with that h and covariant derivatives of the Christoffel symbol associated with that h. We mentioned in passing that, there are references in the notes I put, that this system is weakly hyperbolic, and then we're going to deal with that in a short while. But in addition to that, we have 4 more equations. Here is the so-called Hamiltonian constraint, and this is the momentum constraint, which are to be satisfied at every given hypersurface. So before I go a little bit more on that, let me just make the analogy with electrodynamics and some of the things we could do in electrodynamics. Often we don't do them, but it's something that you could imagine is in your toolbox. And if you feel inclined during this workshop, you could imagine writing a simple code for electrodynamics and testing some of these ideas. So let's go back to that, to Maxwell's equations. I'm going to think of the case without sources. And let me just try and make points here that are 100% translatable to over there. So here we have the evolution equation for E and B. We picture our evolution as such that, well, usually we think we are using a very well-defined system of coordinates. So let me just think of slices like so. We don't typically worry about coordinates. In fact, here, the choices have already been made. I'll show you soon how to write this in a more general framework. There is no shift, nothing. So here is t and x are kind of, in some sense, absolute coordinates. But you do know that if you boost yourself with respect to a particular observer, then you're going to flip, or going to mix E and B. But let's imagine we have defined this coordinate system, and you're going to evolve to the future. So the rules of the game to make things consistent is to satisfy these 2 constraints at a given hypersurface, use those to evolve. But as a choice, as I said, you have these 2 other equations at your disposal. You could think of using them. So why is it that we don't worry about them? Because a consistent solution to Maxwell equations satisfy this, but also satisfy these constraints. In fact, we work hard, in some sense, to evolve here. And we work very hard, I would argue, numerically, to make sure we maintain this. And I'll tell you why. But let's think analytic. As I said, I tend to prefer thinking analytically as hard as I can first, and then fight the numerical fight. So these 2 constraints, let me call it C, E, and CB. So why do we know that if we evolve with these equations, these guys are going to be still satisfied? Well, that we can ask in a trivial way. So let me just use this as an example. Take the time derivative of the constraint. We imagine that we have some error or not in the initial constraints, and we're going to try and ask what happens if I go to the future using these equations, what those equations imply to the evolution of the constraint. So this is the time derivative of dv. So now I can switch the order of the time derivatives. So this is dt of b. I can now use the rule that I'm using to update b, which is to take the curl. So this will be minus, and the divergence of a curl is equal to 0. So we arrive at this condition, and in some corners of the world, this is referred to as the constraint propagate. So you give them, and you initially define them to satisfy or to be given to some given value. If you evolve with these equations, assuming you've done, so analytically, if you evolve with these equations, this tells you that the rate of change of the constraint is 0. So if you satisfy them exactly initially, you're going to satisfy them exactly to the future. Of course, I'm assuming here you have provided boundary conditions that are consistent with the constraints. So we can put aside the boundary condition issues for a while, but make sure we remember that, because you could be feeding violations on the boundary, and that in and of itself is not a trivial question. But let's just think that boundaries are not playing a role. So then if there is no violation initially, these evolutions will not propagate any violation, and you're going to be satisfying them exactly or to the same level that you satisfied them initially. But maybe you could consider other things. So let me just do something that will look like I'm kind of crazy, but it will come and play a fundamental role in what we say later. Of course, this also applies here. I can take the following. I can say, well, how do these two equations propagate, this equation and these three equations propagate? I can take the time derivative of the Hamiltonian constraint and the momentum constraint, replace any appearance of time radius of h or appearance of time radius of k by this rule. And what you find out at the end of the day is that you end up with an equation that propagates the constraints as well. So if you're satisfied at some given level, they should analytically stay satisfied at the same level. We'll see what happens in practice later on. But let's consider changing this equation by the following. How do we want to, let's call it SI. That looks like an act of complete madness. I have this equation, and I added this piece. Analytically, I'm adding a 0, so why would I even consider doing that? But let me push on with that. Again, we can say, we can come in here, ask how is the constraint going to behave if I iterate with that equation, if I evolve B using that rule. So, of course, when I take up to here, it's the same, it only changes here. So I will have equal minus the divergence of the curl of E coming from that term, but now I pick a new term, which is alpha, and let me do this. So it's more messy looking, but now what I have is that the time derivative of C is no longer 0. Of course, this is still the case that is 0. But I have these two terms. Now, dB is my constraint, so let me just write it as C. And this is S times the gradient of C. And for convenience, let me rewrite this in the following way. So it's a contraction of this vector S, which I haven't told you yet what it is. I'm just pulling it out of a hat. It's SA contracted with DI. So let's just try and identify some of the terms where we have acquired by our choice. So first, let me imagine this term. So we have dTC, the rate of change of C, is proportional. Oh, sorry, I shouldn't have used alpha. This has nothing to do with the lapse. We call it gamma. So it's the rate of change of C is proportional to C with this proportionality function, if you want. But if this thing happened to be strictly less than 0, what do you think this equation is going to be doing for C? Any guess? Oh, you guys need to. Second day of the workshop. What are you going to be saying in the 3 months from now, or 2 months? How long is this workshop? So this is, right, it's going to be decaying, because it's an exponential decay of the constraint with this kind of rate. Of course, you have to provide a vector S that has the right properties, but that you're free to choose. You're playing God here, and God tells you do whatever, or you tell yourself you can do whatever you want with that. So that means that as opposed to this case, if you actually started with a violation of the constraint, the evolution will make that violation be less and less. And asymptotically, you could, in principle, approach arbitrarily close the zero case. Furthermore, you have this term. So you have seen this term over and over so far in the past 2 days. And so this is the derivative of this function along S. So this is an advection. So not only is this piece reducing the size of your violation, but this piece is throwing it away. So you might have violations locally for whatever reason next to a source, which may or may be bugging you, and then this net effect is to kind of push the violation aside. Depending on the scenario you're considering, this could be fundamental. So any questions? So this is an example of a total ad hoc trick. In the analytical case where you start with constraint satisfied initially, everything is fine, but numerically you may consider this. And an example is you could, and this is like the constraint transport technique commonly used in astrophysics and other fields, actually rely on writing E and B in a particular way. So E and B are staggered in the grid with respect to each other, so that in spite of errors in E and B, when you compute the divergence of B, you get an exact satisfaction. So the first time I saw the constraint transport, and I don't want to, my tolerance for complicated numerics is very, very low, and I thought this was nuts. If you have to write a code where some of your variables live in one place and some variables live in another place, and you're thinking forward that at some point you're going to use adaptive mesh refinement, and now some center of a grid box will become a grid vertex, I get very confused. I have a more easy time thinking analytically first, work with these kind of things, and then in the end, I can write a code where all grids, all variables live in the same points, and don't have to move around. So again, that's my personal taste. I'm not saying anything against those are techniques. They work, and you should never argue with success. And that technique has been tremendously successful. It's just that to me, it's a bit too much. But just me. I'm a wimp. Not the dark matter particle. So let me just tell you how some of these things come about. So let's see, I'm going to do this now. Let me just stay in Maxwell, and just to confuse the hell out of you, not on purpose. I'm going to write them in terms of, again, the quantities we have defined to write Einstein's equations that way. So Maxwell's equations in fancier terminology can be written this way, and again, I'm thinking of the zero source. So this is a Faraday tensor, familiar to you. Now I'm using the covariant derivative because we are looking ahead. Our space-time is curved. We need to be sure we react to the fact we have to write the proper quantities. We can, given a tensor F, and our vector NA, our metrics H, etc., we can choose to decompose that Faraday tensor in terms of quantities that are normal to the vector N or parallel to it. So this following is true under so for instance, you would have seen the Faraday tensor in the standard coordinates where the electric field occupies the time and space components, while the magnetic fields occupy only the spatial part of the matrix. This is precisely what this is saying, but in general. it's saying that if I take F and dot it with N, that's going along a time-like direction. You could imagine that you choose coordinates where, so they said NA is 1 over alpha ddt A minus beta I dx di A. Of course, you could choose beta to be 0, alpha to be 1, and this N will be just a ddt, the standard thing. So if you replace, you take alpha equal 1, beta equal 0, and you replace in here, this will give you back the electric field just sitting in the Tx1, Txyz column and row. And then this, with a total antisymmetric tensor, which is orthogonal to this and that, will give you that magnetic fields are only living on the spatial part. Yes? Right. So, excellent question. So the definition is implicit here, but let me just give it to you. So E A is F A B and B, and now I'm going to put D here. So you take an F, one of the legs goes with N along N, the argon one goes orthogonal to it, and this, if you use this analogy, or lapse equal to 1, shift equal to 0, this will pick the T, and this will pick the spatial part. Well, that depends. That's an interesting way of putting it. That depends on who the observer is. Exactly. So if I'm the observer parallel to N, this is what I measure for my electric field. If I'm an observer that moves with a fluid that has no relation necessarily to the normal, to the foliation, then indeed, in one frame, the electric field is a combination of electric and magnetic fields, but you knew that already. Right? If you boosted one observer with respect to another one, now the E and B mix each other. Right. So in this case, because of the geometric dynamics picture that we had, it's natural to just keep doing things with respect to the normal to the hypersurface, because you have not chosen yet what other things you could do. But of course, once you relate one field with respect to the other one, then you can just easily do that. And then an example would be if you have your fluid vector has tangent UB, right, velocity, you can always choose to write U orthogonal to N and parallel to N. And we know how to do it because we already introduced two quantities. So we can say, so there's UB and B, sorry, UC and C and B with a minus sign. That gives me the component of U along N. And then the R one would be UB, UC, HBC. That gives me the component of the projection of U orthogonal to N. So now I can also flip this around and write N in terms of U, replace it in here, and then you'll see what the E that one observer measures is related with a different observer. Yes? Here? It is. Yeah. So, yeah, sorry. So if you take these ones, make those replacements, you recover those equations. If kind of the shift is 0 and the lapse is 1, but we keep it more general. But just as we did here, something that is convenient is to consider that I modify the equations. Let me think of the following. And say, well, let's redefine Maxwell's equations this way. I'm shoving in here some 2 extra fields. Why, you'll see as we go along. But let's say, again, if we agree that we would like to choose at the analytical level phi and psi, or however these two guys are called. I don't know, never know how they are called. Then they are not here, and then we're back to the standard Maxwell's equations. But then you could ask, what is going to be the consequence of these guys? So one thing we know is that this stress-energy tensor and its dual are antisymmetric. So if I think of, take grad B, operate with the nabla with the index B. So when I do this, let me only follow one because the discussion is parallel with the R1. So now I have grad B and A. This is symmetric in A and B. Hitting something is totally antisymmetric in A and B. That will give me 0. So there is no contribution of this one. This only gives a contribution that is grad B, grad A. That's that. And then this is the metric that is consistent with grad. So this never differentiates G because it will give me 0. So I can pull it all the way out. This GAB. And this is nothing but the box. So the equations of motion defined that way, with that thrown in, say phi will be propagated as if it were a wave equation. And again, if our initial condition is that we give phi equal to 0, that's the analytic result, we will propagate a 0. So if analytically I gave phi as initial condition to be 0, I had no constraint, no violations, then the induced equation for that constraint will preserve it being 0. So we haven't changed anything. But what I want to do now is to change this. I want to add here so let's say I add that. So now I have a non-zero contribution on the right-hand side. I'm going to pick up here this term. So let me expand it out. So this will be minus k or kappa times, I have a term. Now I have grad operating on n and phi. So that will give me two terms. I use Leibniz distribution. So this will be nb grad b of phi So now this equation changes, and it's equal, it's just this one. So with that change, which again is ad hoc, I just throw it in there. If phi is equal to 0, I haven't changed anything. But then the question is, what happens if phi is slightly different from 0? Well, if it is different from 0, phi evolves under this equation. So here I have the wave operator acting on phi, and I have phi times this grad. So that looks awfully familiar to what we discussed there. So it's an evolution of phi, driven exponentially down, because I have the phi, and also have the grad phi here. So it propagates out by virtue of my n, and it decays by virtue of this. So actually, these two things, these two contributions, are telling us that if we have some initial violation, and we evolve with it, the violation will stay under control, and actually will be decaying. So I would, one suggested problem is that you incorporate, you study Maxwell's electrodynamics, you start some simple scenario where you have, say, a plane wave that is moving around, evolve it numerically, and then try this technique and see what you get. So let me give you now the expressions for the Maxwell's equations, written in the same structure of equations that using the same kind of work that we did to derive these equations. Which will not necessarily look familiar, but you will be able to recognize things. Incidentally, let me just say something I didn't mention. To obtain these three equations, this one was a definition, right? We just defined the extrinsic curvature related to the covariant derivative of the normal vector projected, and that gave us that. That was a definition. These three equations come thanks to something called the Gauss-Kodashi minority relations that relate curvature quantities, in particular the Riemann tensor, in a d-dimensional spacetime with that of a d-1 dimensional manifold within the full spacetime. So that relation is the one that let us write that way. The derivation is too lengthy to do it here, but they are in any textbook. So can I move this blackboard? Yes. So keep these things in mind. Ultimately, these type of techniques play a crucial role in our current ability to evolve strongly dynamical, strong field spacetimes like binary black hole collisions. So I'm just trying to motivate within the context of things that are relevant to this workshop and slowly build back to the Einstein equations. Yes? We're going to evolve psi. So then wouldn't we have to write that in terms of psi so that we can find out? Well, let me give you the equations and we'll connect. So if we take those equations and we do the projections again along the normal and orthogonal to it, we're going to be able to write the following. So let me just write this way. And I'm going to use an Irish shorthand notation first. I'll tell you what it is in a second. Well, I might as well throw this. Okay, so these are Maxwell's equations once you have kind of subjected them to the machinery of this covariant reformulation in 3+1 form. Let's just identify things in here. So first I have to define this. This is a so-called the Lie derivative. So it's related to, remember when we had like the time derivative of h, and then we had terms like beta L dl of h plus h d of beta plus h d of beta. So this piece is a Lie derivative of the tensor H. So essentially, this will give you a derivative along beta plus a few correcting terms, but by and large, it's derivatives of these things along beta. Here it's just beta I di of I. But let's say for the time being, imagine that beta is 0. So you don't have any of these things. You have the time derivative of E, the time derivative of B. Again, think for the sake of the argument that we choose a space-time where the metric H has no time derivative, so we're in a flat space-time. So H is flat, and K is 0, so this will be gone. These two things here, okay, we have the covariant derivative associated to the intrinsic hypersurface, but if we're in flat space-time, this is nothing but the curl. So it's the curl B, curl E. And here is just a gradient of phi along the direction of a vector E. It's our gradient of the R phi, psi, phi. Same thing. So we add a source. We ended up adding a source that knows of phi, I'm psi, or vice versa. So the evolution of E and B react not only by what they themselves are doing, but also what phi and psi are. Remember, psi and psi, those things, measure the violation of our electric and magnetic field distributions of the constraints. So let's look at this. So now we have evolution equations for phi and psi. This goes back to your question. Let's again imagine that beta is 0. Imagine for the time being also that the time derivative of them is 0. If the time derivative of them is 0, so this is no longer here. And here we have the divergence of E equal to the charge density. The divergence of B equal to 0, if we imagine that psi and phi are 0. So this is just endowing now evolution equations to our constraints such that those constraints are driven to 0. So this is a nifty way of rewriting Maxwell's equations such that the possible violation of the constraint is monitored in some sense dynamically, and the fields are driven to modify themselves a little bit to try and continuously drive back to the constraint satisfaction. And on that, I should make the following comment. Suppose there's a, I'm going to just graphically, let's say these are the space of solutions of any E and B that you could with these equations. Let's say, with these equations for any arbitrary phi and psi. They did not satisfy the constraints necessarily. There is a subset on that. I'm going to represent this by some submanifold where the constraints are satisfied, where dE, or let's say dB equal to 0, and the E is exactly equal to the charge density. So we know, so Maxwell's equations tell us, and this is what we described, that if you start with some initial configuration that satisfies the constraints, the evolution will stay within that submanifold. That says, if we start satisfying them initially, we're going to continuously satisfy it. But the question is, what happens if we have initially some violation? We're there. These equations are no longer Maxwell's equations, if we're going to solve with that. We're not satisfying the constraints, so it's something else. It's a new theory. It need not have good behavior. So there is no reason why this thing wouldn't just violently go away from that submanifold. What this correction is doing, or what these modifications are doing, is that if there is a small violation, you bring it back. And if numerical errors, which source possible violations that are continuously being driven, a potential problem is that this driving problem just get the solutions worse and worse. So let me just give you an example, and I'll tell you how this works for Einstein's equations. This works? Yeah. So here, what you have is an example, an old example. In fact, this is a slide for kind of romantic reasons or historical reasons. I even asked Franz Pretorius for this. This is he, as you probably know, he was the first one to solve the binary black hole problem. What went in to be able to solve this is everything we've been discussing about. Going first to guarantee that the solution, the formulation you use, has as good hyperbolic problems as you can. That the derivative operators satisfy the summation by parts. that the dissipation operators are ones that you can guarantee that will take energy away from your system as you require, that the constraints are satisfied consistently initially, but that's not enough. You also needed some old trick, something that Oscar Reula, Hubner, Fritelli, and Brodbeck had written in the mid-90s, and it kind of lay dormant for a while, and it was resurrected by Gundlach and Martin Garcia and Calabrese. And so Franz brought all those things together. And in particular, this thing just made the final thing, was the final ingredient that made the big difference. So this is just to give you an example, illustrates in the left a case as we're going to discuss in a bit. Constrained damping, like so, have been implemented. The other side is the one that doesn't implement it. The subsequent kind of grid black lines that you see will be something about adaptive mesh refinement, but this is for a single black hole. So you have a sequence of boxes in boxes in boxes with further refining as you get closer to the black hole. The black hole has been excised. This was another question. What do we do if you get too close to the singularity? So you cut a hole which is small enough to guarantee that it's inside the black hole. This is something I'll discuss a little bit in a while. So here you put everything, but one side has constrained damping, the other one does not. You tell me which one is which. The black side, that's a hint, has already crashed. That one went away. In a very short amount of time, the constraint just blew up, which again is this clear indication that once you're off the constraint surface, you're solving a different theory. And that theory does not have to have good properties. Even when everything is consistent and numerically correct. In fact, if you were to redo the simulation, and he did that, with much finer resolution, the solution did behave better, did go in the right direction, but it wasn't good enough to evolve for a very long time, a single black hole, let's say. And then once you put two black holes, things also progress in the same way. So this is an example of that adaptive mesh refinement of things we do. And again, I'm not bashing on constraints transport, but constraints transport relies on having this staggered set of variables with respect to each other. But when in a situation where you actually need to bring in many levels of refinement and decide where the new grids are going to be and how you're going to start those problems, we really didn't want to deal with that. It's a lot easier to work harder on the analytical level and then go there. And so far, we haven't had the need to use those kind of numerical tricks. That doesn't mean the future will stay like that. But let me just now jump onto that formulation and tell you a few things. Anyway, so these are some, and someone pointed out, I had written here on the numerical relativity books, there is this one I have forgotten, Eric Gourgoulon. It's excellent, it's really good. Comes from the French mathematical school, so you will see the Frenchiness, the math Frenchiness coming out. It's beautiful. It depends on what your test is. There's a beautiful paper from the 80s, and someone wrote, I'm not going to say who, someone wrote, and one can derive, comma, in the French mathematical sense, comma, the following. I mean, it's priceless. I don't know, coming from South America, I just found it very interesting. It's a good paper. Okay, so now I want to go quickly into the ingredients of one of the formulations, Fein's equations. The other one is very much related in that what we already identified as being a potential problem is dealt with. So remember, we said, so let's go back to the following. So RAB can be written as GCD and I'm going to go in detail on this one, and it will be easy with what we discuss, or relatively easy with what we discuss, for you to read more about the other formulation. Let's say that's RAB. Einstein's equation said that if we're in vacuum, that's a 0. Why? Because remember, Einstein's equations were RAB minus 1/2 GAB, R equal to 0. And I told you what the Ricci scalar is. It's nothing but the contraction, the trace of the Ricci tensor. So if I multiply by GAB, in here, this combined with that one gives me the Ricci scalar. This one combines with that one, just give me the dimension of the space-time I'm working in. So this will be minus 4 divided by 2, R equal to 0. Okay, this is 2, so this says R is equal to 0. So in vacuum, rather than solving GAB equal to 0, one can solve RAB equal to 0 and just save a little bit of room. But it's just a matter of convenience. Like everything I say now can be said in terms of GAB, but it's a bit shorter if we talk about that one. So suppose you're trying to solve this, and we identify, okay, this is pretty good. This looks like just a piece we need for a hyperbolic problem. In this case, notice that I'm not talking about the split. I'm not doing 3 plus 1. I'm talking about the full G metric. We can easily just make the connection, but I'm keeping this way because we're putting everything in the same footing, and some things are much easier. So if you think about this one, this is already given you. Take, again, locally, the metric can be chosen to be flat if we're not sitting, as I said, on top of singularity. So this is simply giving us, again, in Cartesian coordinates, minus dt squared plus dx squared, oops, of GAB. So what we have is 10 wave equations for the components of the metric. And these equations are just as hyperbolics as they will get. So these are symmetric hyperbolic. There is a complete set of eigenvectors. They're all real. They're 1 and minus 1, etc. So this is great. If this were all there is to it with respect to the second order, the principal part of the system, we can ignore this one because it's only first derivative. And I had a question during the break. We're not ignoring it. We're ignoring it with respect to the properties of perturbations locally. Of course, the full solution will be completely determined by, in part, this term. But for the main properties of the equations of motions that we have, we can ignore this part. Here we have the product of Christoffels, but each Christoffel has at most first derivative, so this is still not part of the principal part. We need to deal with this problem. This has coordinates, this has second derivatives of the metric. So what can we do there? So the first thing, so this is, I already anticipated this. So let's say you have already decided you're going to use this kind of derivative operators that these applied mathematical techniques tell you. You work hard now first at the mathematical structure of the equation, and then you identify this being a problem. So let's see how we could deal with this in principle. So one option is to say, well, how many terms I have here? This is a trace of that Christoffel, right? Remember, we had defined the Christoffel. Sorry, no, I just realized you're here and I was joking about, the French mathemat, no. So. So that piece here is you take the trace of these two and then lower the C, or you take the trace of these with the metric if they are all the same, so it's related to this. But there are 4. And how many coordinate freedoms do we have? In a 4-dimensional spacetime, we have 4. So nothing stops us from saying we're going to choose coordinates such that this thing is equal to 0. So this is mathematically oriented. We're saying we're going to choose coordinates that satisfy these properties. We can ask, what does this imply? This implies the following, that if we call our coordinates, let's say, I can even raise the index, it doesn't matter. So this implies that. So if we expand this up, then what we're going to find for our coordinates is this relation. So what we're saying is that our coordinates satisfy wave equations. This is an interesting observation, and this is one of those things that I remember I told you in this field, careful with all wives' tales, or all, what is it, spouses' tales, and I should say in a more gender-neutral way. This thing, in the 50s, Choquet-Brois established the well-posedness locally of Einstein's equation, and she used this one. And she used this one precisely for the cases, for the reasons we are talking about. However, that became a no-no when people started doing numerical simulations. And the reason was, at first sight, it seems very natural. I said, well, I have coordinates that are moving with wave equations. We know what the solutions of wave equations are things that propagate at the speed of light. So if at any instance of time I just happen to have convenient coordinates, a bit later, these coordinates will be moving away from me at the speed of light. So that is a very unfortunate choice. And people put it away, never to be worked with again, numerically. Close to the mid-90s, no, late 90s, David Garfinkel in cosmology said, I'm going to give it a try. And he started noticing that it would work. And the reason is, yes, indeed, these set of equations have perturbations that propagate at the speed of light, but particular solutions that are determined by the lower order terms can stay there time independent. So there were already hints that maybe these coordinates are good. And then Pretorius used them, had to work a bit harder with further conditions here, but the simulations I show you use precisely those coordinates. So that's a kind of a folklore that stayed there for about 3 decades. And if it weren't for someone picking it up and saying, are you sure we understand this? Then it probably people would have been discussing with it. Anyway, so let me just go back to here. So if we take gamma equal to 0, then now we have a hyperbolic system of equations. Everything is great except for the movie I just showed you. It didn't work. Why? Again, it worked mathematically in that if you increase the resolution, things do get better, but not good enough for actually getting the binary black hole simulation. We need one further trick. Let me consider the following. Imagine we want to satisfy this condition, or any condition that you may say, well, 0 might be too harsh for me. I want to still retain a little bit of the freedom. So one thing I could do is to say, you know what, let me promote this thing, which is completely constrained by that, as its own coordinate, as its own variable. So I could say, let me imagine that gamma b is equal to hb. And I'm going to give this by hand from the outside. This looks very odd to begin with, because it is constrained to satisfy that these coordinates better be that. But they're going to be adjusting our coordinates on the fly if I have a good, sensible definition for given these h coordinates, this h conditions. So these are functions. So this would imply the box xa, let's say it's given, or b, is given by that. So if someone, again, if God, i.e. you, give these ones in a sensible way, then the coordinates will adapt, and the contributions here will be independent of the derivatives of that the system is hyperbolic. But there is this constraint that it better be that these gammas satisfy this. So we're going to try to put all this together very much like we did in the Maxwell case. Because I took the trace. So you take the trace here to leave only one index. And so that's what you're doing. You're actually taking, of all these components you have, you take a trace, you have a single one, and that's the one that enters naturally here. So this, in this term, is a trace of the crystal. And conveniently, it's just 4. I mean, it could, if it didn't work that way, then we would have to be doing something else. So let me just consider the following, which is related to things that we have already said, and then you'll see how we're going to play around with them. So let me define that constraint now. I have a constraint, which is so that thing better be 0, because I'm choosing the coordinates such that gamma is defined that way, and then I'm going to evolve it, and I might give my own evolution rule for the h's, and so it better be that this trace of the Christoffels are following it, because that's how I'm defining my coordinates. But we can gain something else with that. So notice that my equation RAB equals 0, the original one, the one where we haven't yet done anything with the gamma, it can be rewritten in the following way. So this is supposed to be 0. I take Einstein's equations, and by fiat, I add this, the covariant derivative of C, symmetrized. What is this doing? Well, this is adding 2 terms. Right? I have this one in the right-hand side. I have it in the left-hand side. Oh, so I have a factor of 2. Yeah, let me divide this by 1/2. So then this one will cancel that one and replace it by that. So we got rid of the offending contribution and replace it by what we wanted. So this is now our equation. Let me imagine that the 2 I absorb in the H so that I don't carry it through anymore. I want to see what the C is doing as we evolve with the equations we get. So let me just tell you a few things. So if you can consider taking the grad, take grad of that, and massage a little bit, not a lot, the terms. If you're interested, I can give you the exact derivation, but in the virtue of time, let me just tell you. If you take the grad of these, massage things a little bit, you end up with the following. So what we did is we're imposing this equation of motion, and now we want to understand what evolving with this equation of motion implies on that constraint C. So we take the derivative, commute, and take the trace at the right time, and then we just arrive to this condition. So this condition says if C is originally satisfied, so if my constraints are satisfied at the very beginning, then this is 0. And so we just have the box of C equal to 0. So this, yet again, is this property that the constraints are propagated by the evolution. So if we have initial conditions that satisfy the constraints we have introduced, which means these coordinates satisfying the harmonic condition or the harmonic condition with some arbitrary sources that we have to give a prescription for, then the evolution will maintain that. By virtue of us having coupled it and put the H is now coming in there as a net effect. But we can do one better. Let me just imagine that instead of this equation, because we added a 0, let's add another 0. Let's consider adding so here what I did is just to add another 0. So this 0 I added such that I could effectively trade the covariant derivatives of gamma with the covariant derivative of H and throw away that term that was offending our property of hyperbolicity. And now add this other one, and we're going to ask what is what is the impact of this. So again, we take the covariant derivative of this. Every time we see a Ricci tensor, we replace it by the grads of C appropriately, and then what we arrive at the end of the day is the following relation. To leading order and I said to leading order in the previous expression you had C grad C, that scales like grad C squared, so I'm ignoring that one. But to leading order, we have this. So again, we have again a wave equation on C is proportional to the grad of n times C times a factor. And if you expand this out, again, you're going to see something that moves away the constraints. So there will be terms out of here that goes like NA grad A of CB. And then there are terms that go like C, B, grad A of NA. So this one produces an advection away from wherever the constraints are larger, so you're just moving them around. And this one makes them decay. Of course, provided you have the right value for gamma. So this was the final trick. And as I said, it wasn't good enough to be with a good, as good as it gets formulation of Ison's equation. It wasn't good enough to be writing the best, if you want, or the most robust derivative operators and time iterators. It wasn't enough to have the adaptive mesh refinement. It was a combination of the right coordinates and this constraint damping. And the beautiful thing is that if you actually remember, or we didn't write them in full, where are they somewhere? No. The constraint equation, so in the case of Maxwell's equations, one could imagine doing something with something that goes like dB equals 0, right? It's a linear constraint, it's a single one. Try doing that with the mess of, say, the Hamiltonian constraint, where you have, it's highly nonlinear and involves many of the quantities. So how in the world would we do that? People tried, and they gave up mainly because things were just too complicated. But so this is a recipe that dynamically adjusts the constraints to better satisfaction as we go along. So now let me tell you a bit about BSSN. So this is the guts or the main properties of the so-called generalized harmonic formulation. This, as an old tale, when Pretorius solved the binary black hole for the first time, he needed to do something with his H's. So he introduced an evolution equation for his H's by hand, being mindful that those H's have themselves also to evolve in a hyperbolic manner. So he introduced a particular wave equation for the H with some adjusting factors. He couldn't solve the binary black hole problem unless those H's were 0. Within 1 year, you could do that. Just having H equal to 0, you could solve the binary black hole problem. And the difference was, when Franz solved the problem, he was at the bleeding edge of what the architectures available were allowing him to do. 1 year later, just a bit of a gain thanks to Moore's law gave you 20, 30% better resolution, and all of a sudden you could set H equal to 0 and things were working.
Sorry, do you mean the point was that you couldn't do the damping fast enough?
No, the damping was working, but the coordinates were not quite able to keep up unless so what he had to do, let me just give you kind of roughly what he had. So he said, okay, I need H equal to 0, it's not good enough. I need some evolution to the coordinates. My coordinates need to adjust a bit more than what they would have adjusted by themselves with the box of x equal to 0. So he said, well, let me give an evolution equation for box of h. I could, of course, put a 0 here, but I want some more. So he started doing many simulations. and realizing that, for instance, the labs at some points were going either too small or too high. So he wanted to kind of fight against that. So he put something like so. So some factor, and so here if the labs got to be larger than 1, this changed sign and did the opposite. If it got to be too close, it shot up. So this times h of t, this is only for h of t. For the hi, he was able to put 0. But for h of t, he needed things of this form. And that allowed him to do the simulation. But as I said, the thing is that he needed a little bit more resolution. With a little more resolution, you can put all of them to 0, and it's fine. But the funny thing is that this happened 14 years ago. To this day, you find people that tell you, oh, harmonic coordinates cannot do the binary. And that's because they read that paper and other papers that follow after. And unfortunately, at least to my taste, computational physics is full of these examples. So the main formulations that people use nowadays is this one, the generalized harmonics. Then BSSN quickly matched up, and then people were able to solve binary black holes. And then, okay, while I erase, I can tell you a story. I think people were awfully close with BSSN to be able to solve the problem. But back in those days, people were fixated to making sure the black holes did not move through the grid. And this is something that in astrophysics applications has been very successful. People use co-rotating coordinates to make sure things stay there, and they have been very successful. So people in numerical relativity were trying to copy that. That meant your coordinate conditions had to work really hard to keep the black hole staying. And they have devised many sort of coordinate conditions. And the moment it's always the case when someone in your class solves a problem, everyone else solves it very quickly, because sometimes they pick up something or they just go past some mental block. And the mental block at that point was giving that away. They said, okay, forget about it. Let's just have the black holes move. And within 6 months, they were colliding black holes. So this is with the BSSN. So the BSSN picks up from ADM. Lots of things that we have discussed for the ADM are the building block of the BSSN, but then it comes awfully close to what we have discussed for harmonic formulation, because the key thing is, again, the same. So I'm going to just give you the basic observations there. So we had the equations written this way, dt of k. And so there are terms where, like beta. So those terms, then you have these terms. Oh, I'll tell you. There's a joke, but I'm not going to tell you that, because it's attributed to me, and I don't think I did it. It's too good to be me. So BSSN stands for the following. So Shibata and Nakamura are in the late 80s, early 90s, realized there was some issue here, the same issue that we discussed. They didn't quite go all the way on the mathematical arguments, but they were already kind of feeling that something needed to be done with this term. Baumgartner and Shapiro, some years later, work a bit more on that, and that became kind of the basics of things. Some of those early things also historically have the connotation that some extra variables are introduced that maybe they're not really there for the right reasons, but they are convenient. And so people kind of latch on to that. But so the key thing is exactly what we just said. We had here essentially a wave equation if it weren't for the second term of this guy. So this guy, just as what we just discussed, it's now HLM, the L, the M of Hij, minus the I gamma j, and then there are things that we would call lower order terms. So, and this is what Shibata and Nakamura realized. Oh, we want to do something with these H's, but in reality, it was more like these gammas. So, one option is to say choose space coordinates where gamma is equal to 0. So this you're staying in the kind of ADM form. We haven't done anything, but choose gamma is equal to 0. That almost buys you out of the woods. You still need to do something with the coordinates. And so this is where a lot of further massage was done to these equations. Part of it dealing with this, and part of it dealing with the coordinates. So I'll tell you a few things. And nowadays, as you said, it's BSSN, so everything I'm going to tell you is now leading into an R formulation, which is almost this. It's called CCZ4. And I have no idea what it's called, but what the CCZ4 is for. So this is a formulation that was derived by Bona and Massot many years ago, kind of taking a page of BSSN, but trying to do something with the constraints. What they were not doing at that point is to try to dump them. They were trying to just keep them on the surface as much as possible, but not dumping. So now this CCZ4, so it's related to the CCZ4 formulation starts from this formulation that we just talked about for generalized harmonic. You take the full space-time, the full equation, Einstein's equations, with these grads that we have introduced, right? The one we just discussed. And from here, you start an ADM-like decomposition, introduce the BSSN kind of split and redefinition variables, and now you end up with essentially BSSN, but with a few extra terms and equations for the violation of the constraints. So if you understand the harmonic and the BSSN, the CCS4 is almost an exercise, a trivial exercise. But it has, as a consequence, as an added bonus, that now you can explicitly dump the constraints. The BSSN by itself controls the constraint, but doesn't do anything explicitly. This one does. So a few things that the BSSN does, and it's partially successful, is to try and make better contact with physics. It makes already natural contact with the geometric dynamics. Because it explicitly uses the 3+1 decomposition, but the harmonic formulation, it only does it for bookkeeping. So what do? So first, you introduce a new metric, which is conformal related. It's a conformal factor. Conformal related to the metric we already talked about, this H in there. So this allows you to measure, given a volume element, this phi is telling you a lot about that. In particular, it keeps good track of where you're close to a singularity or not. And maybe then you can do something. Just very much like in fluid dynamic simulation, where you have these finite volume and methods that are implemented high resolution shock capturing methods, you typically have an atmosphere. And if your density goes below the atmosphere, you kind of do something with it in a very brute force way. This gives you contact with that. I mean, it's hard to do it with all the components of your tensor, of your metric tensor, but if the determinant is blowing up, then maybe you can say, okay, what's going on? And it can put a finger on it. So that's one of the ingredients. The R1 is the introduction of a new tensor A, which is related to our stress area tensor. So it's just a simple redefinition. And the idea here is this is the traceless, and waves are traceless components of the dynamics of Einstein's equations, or the consequence of solving a problem with Einstein's equations. So that gives you a better contact, in some sense, to the possible wave phenomena. And then you introduce, associated to this one, the gamma tilde I j k. And of course, associated to this one, you can take the trace and then write this with respect to gamma twiddle. And the good thing is that this gamma twiddle, after having done this decomposition, is related to the measurement of distortion, coordinate distortion in your grid. So this is an old work by York and collaborators, where they introduce this tensor. This tensor tells you how distorted your grid may be, and depending on that, you may introduce some coordinate conditions that react to how these coordinates are being distorted. So after essentially taking there, doing this, now, once you do these replacements in here, you essentially end up with still that problem, but with the variable gamma twiddle. But now your variable gamma twiddle has a kind of a clean, in between quotes, or a much cleaner sense of what is going on with respect to your coordinates. It's kind of, it's identifying that your coordinates are maybe too distorted, and you could try and react to it. And so what the BSSN formulation is doing is, as it promotes, first it promotes this to an independent variable. The moment you promote it to an independent variable, it's no longer part of the principal part of the second time derivative of h. It's its own entity. Now you have to give it its own evolution. So now this will have its own evolution. You have to provide what that evolution is. And so people have come out with useful gauges, ironically derived to try and keep these black holes from moving from your grid and now letting them go, but monitoring how they are distorting. And then you introduce some coordinate conditions for your shift vector that follow this time variation of this gamma, which in themselves are following the momentum constraints. So it's a bit convoluted, but they are trying to make contact with the physics and your coordinate freedom. That, it also relies, remember I said that the ADM formulation is weakly hyperbolic. If we promote this, we could have done this with ADM. We could have promoted this to its own evolution equation, its own variable, and that would have broken some of the degeneracy, but not fully. You still have a problem that is brought in by the coordinates. So there is also coordinate conditions for the lapse. And usually comes with alpha to some power times the trace of k. And the idea here is that if the trace of k is getting to be very large, you're about to form a singularity or very close to a singularity, and you're slowing down your evolution there so that you have better resolution. And then you use the shift to try and prevent a lot of distortion in your grid. Otherwise, you're just stretching it too much. So all these ingredients are the ones that are used in this in the constraint in the BSSN formulation. And the last two pieces that I should mention, which would not say this is enough because it goes back to the original question, one earlier question, is what do you do when you have a black hole? So with what we discussed so far, we don't have to worry about the presence of singularities if we're dealing with, say, even neutron stars, as long as the neutron stars don't bother themselves to collapse into a black hole. If that's the case, you can put all this thing, and by and large, things are going to work. The problem is, what do you do if you have black holes? So if you have black holes. So there are two primary ways of dealing with it. One is excision. So excision is a very costly but very robust method that basically says identify So you have to identify where are the black holes. If you have them, and then we have to describe, I'll say something about how you identify that you have black holes. But if, then you evolve, iterate some distance inside, and excise. So in the example I gave here, so in here, the black hole is gone from the grid. You cut it out, you cut a hole, and you don't evolve the equations there. Of course, the price you pay for doing that is now you have a boundary. And the question is what boundary conditions you impose there. But if you have done everything correctly, there should be no boundary in there. And again, remember when we discussed yesterday a little bit the issue of boundaries, and if you had a full set of advection equations, which you do because you work really hard at the analytical level to obtain a symmetric hyperbolic system or a strongly hyperbolic system. So you know you can reduce your problem, at least locally, to a series of advection equations. So if all your eigenvalues describe things that are falling into the black hole region, then you don't put any boundary conditions. You don't need to. Not only that, you should not put a boundary condition, otherwise things are going to break. So if I have this, then what you have is this is the outer boundary of your black hole. The black hole is somewhere there. And then things in here are only propagating there. So I don't need a boundary condition there, and they just evolve with sideways derivatives using this summation by parts or however you prefer, and things will just go in and they're lost inside. Of course, I said you better have done your work or at the very least monitor what the characteristics are near the black hole region. Because if any of those is outgoing at the black hole, which would very well happen if you have the wrong coordinate conditions, then it's going to fail. Of course, a priori, you wouldn't necessarily know what is the right boundary condition. You will start with something. Maybe you start with harmonics. You start with the BSSN. And you can always monitor, because people have worked hard to compute the eigenvalues. And you can always check, does the eigenvalue has the right sign? And if so, then you're free to not do something, not try and impose a boundary condition. But as I said, if the sign is wrong, it's not a sign that you have to put a boundary condition. It's a sign that your coordinate conditions are wrong. So let me finish without saying something about that. The other one is the so-called puncture, but it's a misnomer in that you might get the wrong expression. So a black hole has, if you read popular press, can be a portal to another space, another universe. And to some degree, they're right. You could imagine your foliation doing this and going to the Rn, going somewhere else in the space-time, in a space-time that is completely inaccessible to you. And here you could choose to get away with murder. I mean, you can be very nasty here, and then just try to tame. Remember that field I told you there, this phi. If phi is blowing up, what it's saying is you're getting very close to either the other end in space-time, or you're touching a singularity. But if you're close enough, you're inside enough, then you can say, you know what? I'm just going to allow phi to grow to some value, and that's it. It's completely brute force, but you're brute forcingly working inside a black hole, and you can check if anything you do here has a manifestation there. Again, the only way it could have a manifestation is if your coordinate conditions are such that they are moving coordinate effects out of a black hole. That can always be. No one stops you. There's no prescription in general relativity that forbids you from having coordinate effects to propagate at the speed faster than the speed of light. But of course, any observable should be completely independent of that. The problem is that, well, one thing is to have an observable that is independent. The other one is to have numerical artifacts here coming and growing and behaving without bounds. So that's something you need to be mindful of. But for the kind of spacetimes that we're dealing with today, this is fine. This works fine. It relies on representing your initial data in some particular convenient form, which goes back to solving the constraints in such a form, and then evolving to the future, and then these coordinate conditions that people have worked out. The one thing I want to say is, well, how do we know we have black holes? So you know, or if you don't know, let me just tell you. So a black hole is something you never know where they are unless you have solved for the full space-time. Because a black hole, by definition, is the boundary of the region of a space-time that no matter how long you live, you're never going to be able to get signals from inside. So by that, we have no idea if you have a given foliation or a given set of foliation, if you have a black hole somewhere here, because you haven't lived long enough. So what do? Well, we rely on some other result and a conjecture. So first, the conjecture is cosmic censorship. Both these ideas, both these techniques, rely heavily on this conjecture. It's a conjecture by Penrose that says that any singularity is naked from outside observers, unless we're talking about the Big Bang, in which case we have to talk about, well, we are the product of it, and maybe we're inside a black hole, who knows. But any black hole that may be formed by any particular process astrophysically that wasn't there at the very beginning will be shielded by an event horizon. By and large, every time people have tried to find conditions to violate this, scenarios that would violate it, it generally fails. So there are violations, but are kind of very fine-tuned. So we do seem to have a scenario that this is very robust. The other one is the concept for an apparent horizon. So that's a quantity, or it's a concept defined at each individual hypersurface. And we're going to prove a result that says if this is true, this one is always inside that one. Always inside the event horizon. So you know that if you find an apparent horizon, it has to be, by definition, at most at the size of a black hole or smaller. And so what you can do, so this concept relies on take a surface, theoretical closed surface. On that surface, define, so this is a surface. On that surface, you define the normal to that surface. Let's call it SA. And it's a uninormal. Out of that, construct the null normal that is outgoing with respect to that surface. So now we pair it up with n. So we define the vector L to be, say, 1 or square root of 2. So that's a vector that was orthogonal to that hypersurface, but living in the hypersurface. This is a vector that is orthogonal to that hypersurface at that point, and going off the hypersurface. The combination of the two gives us a null vector that points out of that hypersurface. And the apparent horizon is the surface at which, if I compute the divergence of that vector, it's the largest surface where that thing has zero divergence. So what it's physically saying is if you were to be standing on that point and turn on a laser, that light will not be going out, nor will be going in, it will just stay in there. So it's just trapped. So an apparent horizon is the outermost trapped surface. So that's a concept that can be defined locally. It doesn't yet know about where the full black hole, where the event horizon is going to be, because that flash that I just turned, it's neither expanding nor contracting, just hovering here. But we have no way of knowing that if, 100 years from now, someone is going to throw a speck of dust in our region. If that happens, now our region will be slightly more gravitationally attractive, and this photon that was happily hovering at the same distance is now going to fall in. And therefore, it's no longer an event horizon, it's inside the event horizon. Is that clear? So there is, just make sure you take that into account. In a spherically symmetric case, and one of the problems I gave you is to consider a scatter field that is kind of being accreted into a black hole. Consider the full back reaction. What's going to happen there is a black hole is going to grow. So you should be computing the apparent horizon, and you can monitor it. So it will go for a while, it will grow, and then eventually will saturate when no more accretion takes place. And the only thing you can do on the fly is compute the apparent horizon. You wouldn't know what the event horizon is. So let me see. So let me kind of recap of what are the things we try and discuss. So in these 3 lectures, we covered way too much. That I know. I'm happy to have as many questions as you want, whenever you want. But what I try to stress is the full kind of gamut from someone coming from numerical relativity trying to do something that may be relevant to astrophysics, who knows, the astrophysicists will tell, that involves strong field regime, having lived through the pain of nothing working, and the kind of thought and work process that took us to get to where we are. And so we had to clean everything up. We have to understand on the analytical side what sort of problems we had and what sort of freedoms we could bring in to try and help. That's at the analytical level. We went to the numerics, and the numerics identified some sort of recipes that are fairly robust. They are essentially very similar in the thought process to these high-resolution shock capturing methods, where there was a definite problem. A problem was the natural tendency of the system of equations to produce things like shocks, rarefaction weights, etc. And the typical tricks that people were playing before these high-resolution shock capturing methods were just being too aggressive, were dissipating things, and the solution could only be trusted for so long. So there was a significant kind of development there for people to try and get to the point where now you can have more confidence on the kind of characteristics of the flow you're getting. On the flip side, on the numerical relativity side, we had to work, I would say, harder on the numerical, on the analytical side. We enjoy one particular feature, which is our solutions. The solutions of general relativity are not to develop shocks unless you put them in by hand initially. So we could progress much more rapidly from the nothing working to everything working fine for many scenarios, because we know that given a sufficient amount of resolution, not further physics is going to happen below some scales. But in fluid dynamics, you know that further physics will happen. Turbulence will take on, and if you're in 3 dimensions, you're going to just go all the way to this dissipation scale. We have the luxury of not having to deal with that. If you're in vacuum, once you put everything together, okay, you deal with all the problems at the same time. But that's where most of the fun is. And incidentally, I was going to say something as far as before I leave. I put some slides in the repository, but it's related to this ideal MHD. So I'll tell you one example of that. Let me see if I think I have some notes on that. Before I finish, I have 30 seconds. I'm going to take a few minutes just to present, yes. So let me give you a very quick and dirty description of something about ideal MHD and kind of the reaction of someone that comes from my side to some problems. So you've seen these equations a little bit, and you're going to see them a lot more. See, this is in Newtonian, well, Newtonian, not even Newtonian. It's the approximation of ideal MHD. So you have, these are the equations. So if you look at the ideal MHD equations, this is what they are. So they are written, as Pascal was saying yesterday, in conservation form. This allows you to look at and understand that what the solution would be from these high resolution show capturing ways, etc. And you can guarantee that the solution solving for this Rankine, however you pronounce that second last name, is a right solution. The one problem, and this is the case where, and again, I have nothing against this technique. It's just that I have never been able to be brave enough to do anything with it. And I tried to get away as far as I could. So what the constraint transport is doing is, if you actually study analytically the characteristics of this system, what you'll find out is you have one too few eigenvectors. Remember, I stress that's where we want to go. This one is lacking one. So in the kind of the composition of this matrix, you're going to see a one sitting off the diagonal. And we already talked how badly that could be. Turns out that you can recover that extra eigenvalue or eigenvector if we enforce dB being 0. Some of these things will just go away. So if constraint transfer enforces dB exactly, say at Randolph level, being satisfied, regardless of what the numerical errors might be. Maybe that your each individual field has a very large error, but dB is equal to 0. So that's one. Oops. That's that system. However, as an example, and maybe as a thought-provoking thing, I don't know when it was, but Powell, I think it's the early 90s or mid-90s, said let's add something to the right-hand side of these equations by fiat again. So he's going to add things like so. So instead of 0, you're adding this. This is proportional to dB. If this is 0, you have added nothing at the analytical level, right? But now you can come and say, how many eigenvalues and eigenvectors do I have in here? And you have all of them. So now, without this, you can recover a system that mathematically has all the properties you want, except for one. In this case where shocks happen, and you're trying, you have an infinite number of possible solutions beyond the shock, and you picked a unique one by looking at the weak solution that satisfies entropy conditions and these jump conditions. Many of those discussions rely on not having a source term like this that involves the evolution variables you're dealing with. So you gain some and you lose some. So if you add this, you gain a lot on the mathematical structure, but you lose some also on the mathematical structure, that is not being able to 100% be confident the solution you're obtaining is that unique solution. Of course, numerical studies or thorough studies of your numerical solution could tell you whether it is, but this is something you need to do. Of course, the gain that you have at the end of the day for some of us is sufficiently strong to say, well, I'd rather work on this because I don't have to stagger variables with respect to this mess. This system is already messy to begin with. But as I said, there are many useful, very successful simulations with this that has no problem whatsoever. You have this, however, this fixes that. But if you have an initial violation, again, we learn that we would like to keep it under control as much as we can. And then you can add to this constraint dumping. And we can take a page of what we discuss. Yes? Yeah, that's a good question, but there are similar problems there as well. But, I mean, yes, I think maybe more attention should be paid that way, but I wouldn't be able to say much of that. There are some physical conditions that are quite natural to be implemented at the level of the electric and magnetic fields. In fact, notice that I don't have an electric field already here. That assumption has already been built in. I don't know how it works on that. I'm pretty sure it can be done, but it might not be as natural. Maybe Charles knows. But one can add constraint dumping very much in the same way that we added in the case of Maxwell's equations. We can add another field, So you usually add one field per constraint that you want to dump. You add an ad hoc equation to that field to make sure you drive it to 0. And as it gets driven to 0, you also are driving the constraint to 0. So it's a way to combine these. And I would suggest there is a very nice presentation by someone named Lehner, but I can give you some references, and I have them in my slides somewhere, that kind of presents a hyperbolic way of doing this. And some of us are using this routinely, but as I said, there is a lot of variety here. And I think it's very arguably the case that this camp, the camp that uses formulation, is far ahead in the number of problems that have dealt with and have studied with good success. But anyway, so just to say, there is everything we've discussed. There is a parallel in other problems, and especially as a young person coming into the field, I would say just beware of all spouse's tales. Whenever someone is telling you something that comes from computational physics, just pause and think, is it really true that we need to go this way? Thank you. Any questions? Higher order constraint transfer, I think.
You higher than second order in space with constraint transport? Yeah. You just, so I haven't been involved in writing these, but I think it's
Jim?
now has a third order.
That works with mesh refinement as well?
Yeah.
Okay. All right, thank you.